we saw what an algebraic integer is in the earlier lecture, and we proved some of its properties. Now, we want to look at the set of all algebraic integers, and the first thing we will show today is that the set of all algebraic integers in a given number field forms a ring, and then we will start studying properties of this ring. Okay. Let K be a number field So, definition OK, at first this is just a set, this is all alpha in K such that alpha is an algebraic integer. Okay, so this is a subset of K, and the first thing we are going to show about this subset is the following proposition. This is essentially corollary of what we proved last time. OK is a subring of K. Okay, I recall definition of a field for you, but I am not going to recall definition of a ring. Anyway, that is I assume that all of you know what a ring is. So, here is a proof, a quick one. So, let alpha and beta be algebraic integers. We want to show that alpha plus beta and alpha minus beta and alpha times beta are also in OK. Okay. So, to show something is a subring, you have to show that 0 is contained in that ring, 1 is contained in that ring, and if you take any two elements of that ring, then it is closed under addition taking additive inverses and under multiplication. So, it is clear that 0 and 1 are algebraic integers, and so they are in OK. So, the only thing to show is that if you take two algebraic integers, then their sum, their difference and their product are also algebraic integers. Okay. So, how do we do this? Well, we consider Z alpha beta, okay, and we will show that this is a finitely generated Z module. So, we know that Z alpha and Z beta are finitely generated Z modules. Okay. So, say 1 alpha up to alpha to the m generates Z alpha, and 1 beta up to beta to the n generates Z beta, then it is clear that 1 alpha squared up to alpha to the m beta alpha squared up to beta alpha to the m and so on up to beta to the n beta to the n alpha and so on up to beta to the n alpha to the m. So, how do I write this as a set? This is simply alpha to the I, beta to the j, such that 1 is less than or equal to I less than or equal to m, 1 is less than or equal to j less than or equal to n. This generates Z alpha comma beta, right, because Z alpha comma beta are polynomials, two variable polynomials evaluated at alpha comma beta. Okay, two variable polynomials over Z evaluated at alpha comma beta. Now, in this particular ring we have these elements. Okay. And we know that submodule of a finitely generated module is again finitely generated, because Z is a Noetherian ring, right. So, some things from abstract algebra that I am using here from ring theory. So, hence Z alpha plus minus beta and Z alpha beta, these are contained in Z alpha comma beta, are finitely generated over Z. Hence, they are also, by the result that we proved last time, they are also in OK, they are also algebraic integers. Okay. So, we have proven that OK is a ring. Okay. So, this ring OK is called the ring of algebraic integers in K. Okay. And so, it is useful to keep the following sort of diagram in mind. So, Q is at the base and then K is a finite extension of Q. Inside of Q we have Z, these are integers, and the analog of this in K is OK. So, inside of that we have the ring of integers OK, and you should think of OK as an analog of Z. Okay. So, that is why they are called algebraic integers, and we are going to prove a bunch of properties of these algebraic integers. So, in this course we will prove the following things about OK, and this will take, I mean not today, but this will take several lectures, essentially whole of the course, to prove these. So, amongst other properties, the main things that we are going to prove is that OK is a Dedekind domain. So, we know that Z is a principal ideal domain, the ring of integers is a principal ideal domain, but OK is in general, for a general number field K, is not a principal ideal domain, not necessarily a principal ideal domain, but we will prove that it is a Dedekind domain. So, in particular every non-zero ideal of OK will be a product of prime ideals in a unique way. Okay. Since it is a Dedekind domain, we will see that you can define ideal class groups for Dedekind domains, and for rings of integers of ideal class group we will show that ideal class group is a finite group. So, in general for a Dedekind domain, ideal class group need not be finite, but for ideal class group of these particular Dedekind domains, the rings of integers, we will show that they are finite. OK cross, the ring of the group of units in OK, so these are units, we will prove that this is a finitely generated Z module. So, this is called Dirichlet's unit theorem. So, we will prove this, and then we will do a bunch of computations. So, for example, finding integral basis of OK, ideal class group of OK, etc. Okay, so, we will look at all these things over this course, right. So, our main object of study is actually the ring of integers in a number field. Okay. All right. So, but we will have to look at some generalities first. So, let me give you these generalities. So, definition. So, we saw the definition of what it means to be algebraic over Z, but just as we can define algebraic over any field, we can also define what it means to be algebraic over rings, and so that is what I am going to do now. but just as an analog of Z, these are not called algebraic, but they are called integral elements. So, let R1 be a ring, let R2 be a ring containing R1 as a subring. Okay. So, R1 is contained in R2 as a subring, okay, not just as a set, but also as a subring. Alpha in R2 is said to be integral over R1. So, this is very similar to what I defined last time about being algebraic over a smaller field, but in case of rings, in context of rings, these are called integral elements, is said to be integral over R1 if there exists a monic polynomial f of x in R1 of x, so with coefficients in the smaller ring, such that f of alpha equals 0. Okay. So, integral over z just means algebraic integer. Okay. So, that is this is a generalization of that. Now, we say that R3, okay, let me define it a bit differently. Integral closure of R1 in R2 is the set of all alpha in R2 that are integral over R1. Okay. So, integral closure of R1 in R2, this is all alpha in R2 such that alpha is integral over R1. Okay. So, I am just repeating myself and I wanted to write it as a set. Okay. So, that is the integral closure, and so what it means to be integrally closed. So, we say that R1 is integrally closed in R2 if R1 equals its integral closure. In R2. Okay. So, you take all elements of R2 that are integral over R1. If the set you get is equal to R1, then we say that R1 is integrally closed. So, every element of R is of course integral over R. Right. So, given that, so why is this definition important to us? Well, we prove the following. So, OK is integrally closed in K, right. So, why is this important? Let me recall the diagram again. Okay. So, so OK is the set of all elements in K that are integral over Z, right. But there may be a priori there may be more elements of K that are integral over OK. The lemma is saying that this does not happen. Anything in K that is integral over OK is also integral over Z. So, that is a very nice thing, because then it really tells you that this is an analog of Z. You can't you can't keep taking integral elements and you know form a chain like that. So, how do we prove this? So, let alpha be in K and integral over OK. So, what does that mean? There exists f of x in OK of x such that f of alpha equals 0. That is what it means to be integral over OK. So, f of x is monic, etc. So, f of x is x to the n plus a n minus 1 x to the n minus 1, so on up to a 0 in OKX, right. All right. So, this means that a n minus 1, a n minus 2, etc. up to a 0, these are all in OK. So, in particular this means that z a n minus 1, a n minus 2 up to a 0 is a finitely generated z module, right, because these are all algebraic integers, all the ai's are algebraic integers. So, by the property that we proved about algebraic integers, this is a finitely generated z module, right. So, let us say this is generated by say generated by S, by a finite set S. Okay. Now, over this z a n minus 1 up to a 0 and alpha is generated over z a n minus 1 up to a 0 by 1 alpha alpha squared up to alpha to the n minus 1, right. This is simply because alpha is a root of this polynomial f. Right. So, we saw this earlier when we proved in those 3 equivalent statements, we proved 3 implies 1. Okay. So, hence z a n minus 1 up to a 0 and alpha, sorry, let me write it properly, is generated over z by the following set S union alpha times S union alpha squared times S and so on up to alpha to the n minus 1 times S. So, what does this mean alpha times S? It just means that I am taking products of alpha with every element of S. This is a finite set. So, hence alpha is an algebraic integer, but OK was the set of all algebraic integers in K. So, hence alpha is in OK, right, which means that OK is integrally closed. So, that is a nice thing because we do not get any, by taking integral closure of OK in K, we do not get any new elements. So, OK really is the analog of integers in K. Okay. All right. So, so moving on, we want to prove further things about this now. All right. Yeah. So, the next thing I want to tell you is, so now what we did was we defined what a number field is, then we defined what algebraic integers are, studied properties of these elements, then we studied properties of all the algebraic integers taken together. So, the thing we proved that it forms a ring. Now, we want to consider this ring of algebraic integers as a sub ring of the number field and we want to study that, right. So, one obvious way to proceed is the following. So, let K be a number field of degree n. Okay. So, this means that degree of K over Q is n. After fixing a basis, fixing a Q basis of K, we can identify K is isomorphic to Q to the n as vector spaces. Okay. Not, of course, not as field, because Q to the n does not have any natural structure as a field. So, this identification is just as identification of Q vector spaces. Okay. And now OK is contained in this Q to the n, right. So, you can ask yourself what is this, so you can ask yourself what is this OK? I mean, how does this OK sit inside this Q to the n? So, roughly you can think of Q to the n as rational points in R to the n, and R to the n is a nice Euclidean space that we are used to from linear algebra or from coordinate geometry, etc. And so you can think of it as, you can visualize it geometrically, and you can ask yourself how does this OK sit inside this Q to the n. For K equal to Q, we know that integers, they are just discrete points on a real line, right. So, even if you consider Q as a subset of R, Q as a subset of real line, Z are just discrete points. So, you can ask if something similar is true about OK, and indeed it is. So, we are going to prove the following proposition, but for that we will need some preparation. Let me state that proposition anyway. So, after identifying K with Q to the n, we get OK as a lattice in Q to the n. So, a lattice is a discrete subspace, discrete Z module in Q to the n which spans Q to the n. So, I will define what a lattice is in a minute, but the upshot of this proposition is that just as Z sits discretely as discrete points in Q, even in this more general Euclidean space, OK sits as a lattice. So, these are discrete points. So, the standard lattice that you think of is probably you take the R2 and then all the Z2 points, all the points with integer coordinates is a lattice in R2, right. So, it is something like this, but the shape may be more complicated, and we will come to the description of the shape after in due time. Okay. So, let me tell you first about norm, and then I will tell you about lattices, and then we will prove this proposition. So, this will take some time. So, let us recall norms and traces. So, I am saying this as recall because you should know this from your field theory course. Okay. So, now we revert back to general extensions of fields. So, let L over K be a finite field extension not necessarily number fields at the moment, but in the end we will study this mostly in case of number fields. Okay. Then as we know, L is a K vector space and it is a finite dimensional K vector space. So, you for any y in L define the following map, define a map from L to L which takes any x to y times x. So, this is a K linear map, this is a K linear map. Right. So, if we fix, if x1 up to xn is a K basis of L, then y times xi you can again write in terms of K basis. So, y times xi is again an element of L. So, you can write it in terms of this basis, and the way to do this is from j to n aij xj for some aij inside K. So, what happens is consequently we get a matrix. So, A equals aij, this is a n by n matrix with coefficient in K that represents this linear map that takes x to y times x, this K linear map that we have on the previous page. Okay. So, characteristic polynomial of y is defined as follows. So, f of y, maybe I should write it as f of x, this is determinant of x times identity minus a. Okay. So, I here is n by n identity matrix. Okay. And so, this is the usual sort of characteristic polynomial that we see in linear algebra. So, f of x, so exercise is that f of x is independent of the choice of k basis of L. So, this is again you must have seen in linear algebra that the characteristic polynomial of any of a linear map is independent of the matrix representing it or the basis that you have chosen. Okay. Anyway, so this characteristic polynomial is a useful thing, but we are only interested in the two coefficients of it. So, you define trace from L to K of y to be trace of this matrix A. Again, it is independent of the choice of basis. So, this is the coefficient of x in this f of x, right, up to maybe sign up to sign, and then norm of y. So, norm from L to K of y, this is simply determinant of A, and again this is independent of the choice of basis. So, independent of the matrix A representing a linear map, this linear map that we have. So, here is an exercise. If y1 and y2 are two elements in L, then prove that trace of y1 plus y2, so trace from L to K is same as trace from L to K of y1 plus trace from L to K of y2, and norm from L to K of y1 times y2 is product of the individual norms. So, norm from L to K of y1, norm from L to K of y2. Okay. I will give you a couple of more exercises because this is all from linear algebra. So, exercise. Right. So, L over K be a finite extension and M over L be a finite extension, and let Y be an element in L, the intermediate field. So, you can now define characteristic polynomial of Y with respect to the extension M over K or with respect to the extension L over K. So, let f f of x and f of x be characteristic polynomial of y with respect to extensions M over K and L over K respectively, So, are these related in any way? That is the question, and that is the exercise that I want to tell you. Then prove that f of x is small f of x to the power degree of m over L. Okay. All right. So, so that is an exercise, and then the next piece of exercise that I want to give is the following. Okay. All right. So, so let L over K be a finite separable extension. So, this is kind of necessary, the separability, and again, since I am assuming familiarity with field theory and Galois theory, this is a standard notion in Galois theory. So, I am assuming that you know what a separable extension is. Let Y be an element in L. Okay. Consider this field Ky contained in L. So, this is the smallest field containing both K and Y. Okay. So, you look at all the rational, you look at quotients of all polynomials f of x over g of x with coefficients in K, and then you evaluate them at Y, provided that g of y is not 0. So, those are the kind of elements that are in Ky. So, that is a more concrete description of what Ky is, but a more conceptual description of what Ky is that it is the smallest field containing both K and Y. Okay. So, let sigma 1 up to sigma m be embeddings of Ky inside K bar, all the algebra. So, so again for this exercise I am fixing algebraic closure K bar of K. Then I want you to then prove that trace from L to K of Y is degree of L over Ky summation I going from 1 to m sigma I of Y. So, maybe this is a more, you may have seen this description, this definition of norm before or not, I do not know. So, this is product I going from 1 to m. So, slightly more general or slightly different than what I have than what you may have seen before, but if you saw definition of norms and traces in terms of embeddings, but it amounts to the same thing. Okay. So, again this exercise we are not going to directly use anyway, it is just about embeddings. So, norm is a product of some sort, right. I mean originally we defined norm as a determinant, but here it is a product of some sort, and that is going to be useful for us. Okay. So, what we did today is we looked at the ring of integers, and we want to show that the ring of integers when you identify the number field k with Qn, the ring of integers is a lattice in Qn, and as a preparation for that we saw what norm and traces are, and next time we are going to look at what lattices are and prove their properties. So, then we can go back to proving the proposition that we want to do, that OK is a lattice in Q to the n, and then we will study that lattice.